Hello everyone, welcome back to Power System. This time we're doing class 18 and we're going to talk about Newton-Raphson method. This is the method to solve nonlinear equations, all right? And it's an iterative method. That means it's going to go through iteration to find the solution. And when you use numerical analysis to find the solution, you're not finding the exact solution, you're finding the solution very close to the exact value. And also going to talk about constraint parameter optimization in part 2. So Newton-Raphson method. What is Newton-Raphson method? This is the this is the function over here, right? We're trying to solve this function. We're trying to find the value of x that satisfies this solution, right? But to use the Newton-Raphson method or numerical analysis, we have to guess a solution. So that's why we're estimating the initial solution is x. 0, this is my initial estimate, then obviously that is not the exact solution. So that means your exact solution x is my estimation plus delta x0. What is delta x0? Is the difference between exact solution and estimation. So delta x0 is the difference between estimation and exact solution. What are the 0 here? This 0 represents is my initial estimation. Then after you go to the process, it becomes 1, 2, 3, and goes on until you get the solution, right? So with that, you know Taylor series. Taylor series, you can expand a solution, extend a function at a point. So I'm expanding this function over here at x0, that's my initial estimate. So if I do that, this is the Taylor series expansion, you all know that. And again, delta x right here is the same thing over here. So if the delta x very small, that means my estimate is very close to the actual solution, all the higher order would be 0, right? That means this is 0 and all other higher would be 0. So this becomes a linear function, also these terms over here, right? So I can find over here the delta df dx, right, 0, and delta x 0 equal to c over here minus fx 0, right? So, and also this term over here is called delta c 0, right? This is the difference between your c minus the function value at initial estimate. So if this is 0, that means you reached the solution. If this is 0, that means you reached the solution, right? So over here now, same thing over here. So delta c0 and this term over here. So from here you can easily find delta x0, which is basically delta c0 over df dx0, right? So once you find the delta x0 from this equation over here, you can add that value to an initial estimate to find the next one. That means you're adding this to your initial estimate to find the next solution. So initial estimate was x0 plus delta x0 will give you the next solution over here. So that is right here, right? So then, and once you find the x1, then you can easily find delta x1 here is same process. Then add that to delta x1 would be delta c1 over df dx1, right? Then you can add that to your solution 1 to find the next solution. Right? So, and you can see that the general format here, xk plus 1, right, would be xk plus delta xk, right? So now your goal is to find delta x or the different mismatch between the actual solution and the estimate. So when you're like two solutions close to each other, or your function value becomes 0, you reach the solution. Either your function x close to 0 or your two solution over here 0. If any of this condition meet, then meaning you reach the solution, right? So let's see how can you apply this to the problem. So we have the same problem here from before. This is the x and y. value you have seen from there. And this is your function in terms of lambda. You have three functions. Remember the three partial derivative in terms of lambda. We're using x and y value here to make the function of lambda. So you can put x and y value from here to here, and here you get the function of lambda. So you're trying to solve this function. We're trying to make sure that at what value of lambda will make it 0, right? That's the goal here. So what value of lambda will make this function to 0, okay? And if you find the lambda function, then you can find x, y value too. Over here, look at that. C is 0 here. You can remember the C is 0. So that means your delta C K would be 0 minus your F, right? Lambda K, right? We're calling it delta F lambda K. Negative delta F lambda K. We're calling it negative delta F lambda K. All right, there's a only change over here because C equal to 0, right? So that's right here. So negative delta F lambda K. And this is, we also call it in your code, we call it J. So that is the value in your equation to find del lambda K. And if you know the F lambda, if you take the first derivative of lambda, it becomes this one over here, okay? All right, so, and your goal is to find this one, right? And if your solution didn't meet the category, you go back and find the next solution and use it again and again. So we're gonna put it in a while loop to do all these things. So first of all, we're starting with iteration 0, and your delta F or df over here, we take it 10. That means delta F needs to be 0, right? Look at here, delta F needs to be 0 to reach the solution. So I'm starting from 10 to get into the loop. Then your lambda, you can put an initial lambda, you can enter a value for lambda. Then your printf, what do you call it, next line. Then you're displaying all those parameters, displaying iteration, you're displaying function, you're displaying j, d lambda, lambda, and all those values, and x and y, right? So you get in the while loop because we have a df is 10, which is higher than this one here. This ideally should be 0, but we're doing it 0.001, it's very close to 0. So that's df right here. This is the df right here. So it's ideally should be 0, but we're doing 0.001. Then iteration plus 1. Then you can find x and y value from the equation we just saw in last slide. Then df is right here, right? You have x and y. So I can put x and y in there directly to find df, right? That should be 0, right? Then j is basically right here, right? So we got that one there. Then del lambda right here, del lambda, you find, so your del function divided by j, negative del function divided by j will give you the lambda, del lambda over here. Then you can display all those values again. Then you go to the lambda over here, so you can use this equation to find next lambda, lambda plus del lambda, and so on. If you go back again and again until your df over here is very close to 0, then you stop it. That's what your goal here. Your df should be equal to 0, right? Then you will not go into the loop anymore because of this condition over here. Then you'll spit out all the solution right here. So we started with lambda value 0.4. Then you saw that once we solve all the problem here, look at that is become 0. Then you have the xy value over here for the solution. All right. So that's all for that part. We're going to talk about this in the next video.